Okay, so let's work through a full example and show how you would determine how to hybridize what's on each atom, what to include in your pictures, how to figure out what pictures you need, and get all of the drawings of our hybrid orbitals. So we're going to sketch the sigma and pi framework for CH2O. You need a Lewis structure, and this ends up being something that's trigonal planar. So I'm going to put all of this together in one picture, but you could go, knowing that carbon is your central atom, and build up from there. So I have carbon, 2 single bonds to hydrogens, oxygen, double bonded to that carbon. Oxygen has 2 lone pairs. So the geometry around carbon is trigonal planar. We would expect bond angles of 120 degrees. They're probably pretty close to that. The other thing I will need to consider is what's going on with oxygen. So this is where what we do will differ from what you might see in some textbooks. We will hybridize every atom that we can, so anything that is not hydrogen. So for my oxygen, you should be able to convince yourself that this has a steric number of 3. And we're going to need that in order to do our pictures. So the way that this molecule is drawn, it would be in the XY plane. Now I am going to rotate it for reasons that I can think about now because I know what's coming. It would be totally fine for you to do this with it in the XY plane and leave it and then go from there. So what I'm going to do though is I'm going to put it in the XZ plane. So I've rotated my molecule. It's kind of laying flat on the desktop, flat on the ground, however you want to think about it. And so I've got a hydrogen going back and a hydrogen coming out. Carbon double bond to oxygen in the plane going to the right. So for each atom, I'm going to figure out the steric number, which will tell me what the hybridization is. So carbon has a steric number of 3. That means I need to use 3 orbitals to make my hybrids, which is the S and 2 of the P's. So steric number of 3 gives me sp2, and I have a p orbital left over. For oxygen, it's the same. I have a steric number of 3. I have one atom connected and 2 lone pairs. So my oxygen will also be sp2 hybridized, and I'll have a p orbital left over. My hydrogen, it only has that 1s orbital, so I can't hybridize it. I'm just going to use the 1s orbital to make any bonds that hydrogen needs to make. So the next thing that I think is helpful for keeping track is that you can make a list of the bonds that you need to make and then which orbitals would point at each other to overlap to make those bonds. So for an example, probably the shortest one to figure out, a carbon-hydrogen bond. It's a single bond, so it's a sigma bond. So for carbon and hydrogen, my carbon is using sp2 hybrids. Hydrogen is just using the 1s, and it is a sigma bond. And then I have in parentheses here, my sp2s are going to be made with S, px, and pz. So how do I know this? Why do I need to know this? I know this because my molecule is in the XZ plane, so that's where my bonds have to be, so I have to use the orbitals that would make up that plane. All right. So both of my carbon-hydrogen bonds will be carbon sp2, hydrogen 1s sigma bonds, and my carbon sp2s are going to be made with S, px, and pz. On carbon and oxygen, I have a double bond. So I have 1 sigma bond and 1 pi bond. My sigma bond, it has to be orbitals that point at each other. So because of what the hybrids look like, it means that the hybrid orbital is going to overlap with the other hybrid orbital. So that's a carbon sp2 and an oxygen sp2. I already know my carbon sp2s are made with s, px, and pz. My oxygen sp2s have to have at least some component that makes it overlap. Now, I am also going to make these with S, PX, and PZ so that, as you can see on the next line, when I make the pi bond, I have the PY available on carbon and the PY available on oxygen to overlap side by side, which is what a pi bond is. It's that sideways overlap. I need to use a regular p orbital to do it, and I need them to point both in the same direction. Okay, now you might feel like you're done. There's one more thing that we're going to account for, which is the oxygen lone pairs. This is considered part of the sigma framework. So, right, there will be a reminder, but when you do the sigma framework, you're going to do all single bonds. You will do one of the bonds if you have a double bond or a triple bond. You'll do the sigma one, and all lone pairs. And they live in the sp2 hybrids on oxygen. Okay, so let's sketch pictures of these. So my carbon sp2 hydrogen 1s. What I'm going to do is draw the structure of the molecule, at least in some basic form, even if it's a single line connecting everything. Make sure that perspective is shown if you have anything that's not flat in the paper. And then I'm going to draw in one interaction. So I'm just going to draw in this carbon sp2 hybrid overlapping with the hydrogen 1s to do a sigma bond. And right, like I have done my best to show perspective here. It gets difficult to do so. Do the best that you can. So I've got my outline kind of bold on this hybrid orbital to show that it's coming out at me. My other carbon hydrogen sigma bond is made up the exact same way. It just points toward the back. So instead of drawing it, I'm just going to write plus one more. Those are my carbon hydrogen sigma bonds. My carbon oxygen sigma bond, again, I have the whole molecule here, but I've only drawn in one interaction, which is the sp2 on my carbon pointing at the sp2 on my oxygen, right? One of the sp2s. So for carbon, it's the one that I haven't used for my carbon hydrogen bonds. For oxygen, it's the one that points at carbon, right? We need them to point at each other and constructively interfere. So carbon sp2, oxygen sp2 sigma bond. That means the only thing I haven't drawn for my sigma framework are the lone pairs. So my oxygen lone pairs are in sp2 hybrids on oxygen. So just like with every other picture, I'm going to draw the basic outline of the molecule, and then I'm going to put in the correct orientation and angle and direction and perspective the proper orbital for this lone pair. So on oxygen, it's an sp2, and it's an sp2 that's in the xz plane. So since I showed the perspective of something in the xz plane coming out with that carbon hydrogen sigma bond, I've shown this one going back, like behind the board, behind the paper, behind the screen. Again, it's not perfect, but this dashed outline communicates that perspective-wise, this would be pointing back. Now my other lone pair is in the exact same type of orbital, so thankfully here I can also do a plus one more. What's left over, or the only interaction, the only part of this molecule being held together that we have not accounted for, is the pi bond. So in the pi framework, it's my carbon-oxygen pi bond. This is made by the p orbitals overlapping side by side. And so that is what I'm going to show here. Outline of the molecule, a regular p orbital on carbon, a regular p orbital on oxygen. If you accidentally draw your carbon and oxygen too far apart and your p orbitals don't touch in the picture, you can just connect them with a line to show that this interaction is happening. Okay. Second example, we're going to do a sigma and pi framework for acetylene, which is H attached to carbon with a triple bond to another carbon, and that carbon is connected to a hydrogen. So I've got this on my axis system. I'm going to go through and do my steric number and hybridization for every atom. So my hydrogen, well, it just is going to use the 1s, it's not hybridized. And then my carbons, each carbon is connected to two things, right? It's got a carbon on one side and a hydrogen on the other, regardless of the number of bonds. So that's a steric number of 2, which is an sp hybrid. And with the way that my molecule is drawn, this is along the x-axis. I'm going to need my hybrid to be made from S and px. So they'll get smashed together to make the hybrid that points in the right direction. So my sigma bonds, I've got a hydrogen 1s carbon sp sigma bond on the left. The one on the right would look identical, so I'm just going to say plus one more. And then I have one carbon-carbon sigma bond. It's a carbon sp overlapping with another carbon sp to make a sigma bond. And that's it for the sigma framework. Single bonds to the hydrogens. Out of the triple bond, only one is a sigma, and there are no lone pairs. For the pi framework, I have py and pz left over on each carbon. So the overlap of one set of orbitals will give me the first pi bond, and then the overlap of the second set of orbitals will give me the second pi bond. So I will have a sigma and 2 pi's, so that's 3 bonds in total. So the pictures, the py pi bond is this first picture on the left. So with my molecule, right, my py orbital centered on each carbon, pointing up and down, overlapping side by side, and my pz pi bond coming out and going back on each carbon, overlapping side by side.